This will be the Chapter 8 Chemical Bonding Notes for AP Chemistry. We're going to quickly go through the slides that we do in class. First thing we talk about are chemical bonds holding atoms together, and they come in three types. The first type of chemical bond is an ionic bond, and it's the static force, the electrostatic force that holds ions together. For example, you have a sodium with a positive charge and a chlorine with a negative charge, and they're electrostatically attracted to each other, and that's what keeps sodium chloride together. And also you have potassium bromide, again positive and negative charges keeping the molecule or the ionic compound together. Then we have covalent bonds, which are keeping atoms together when they share electrons. So for example, we have a hydrogen molecule made up of two H's, and they share one electron between them, and that's what keeps this molecule from falling apart. The next example is NH3, which is ammonia, and the nitrogen is sharing one electron with hydrogen. It's actually an electron pair that's being shared. Nitrogen has one electron in the pair, and the hydrogen donates another one to make the pair. And when they share those electrons, it keeps them from falling apart. Metallic bonds are the third type of chemical bond, and it's a little more obscure than the ionic and covalent bonds that we talk about. And it refers to metal nuclei floating in a sea of electrons. So you basically have positive nuclei of the metal, like copper as an example, or gold, and they're surrounded by a sea of electrons, and those electrons are pretty mobile, which gives metals a strong tendency of conducting electricity and heat. On the next page we have the Lewis dot structures for the elements, and if you want to represent the electrons that are in the outermost shell, these are called valence electrons. You can just basically look at the group number on the periodic table. Now I call it the group A number because some periodic tables number from 1 to 18, but in my classroom I have a periodic table that numbers group 1 and 2 as 1A and 2A. Then it skips over the D block, and then you have 3A, 4A, and 5A all the way to the noble gas row, which is 8A. So if you look at the group number, that's going to tell you how many valence electrons there are. And if you want to worry about the D or F block, which we don't too much, they only have two valence electrons, which are the S electrons in their outer shells. And helium is an exception to this group A rule because it only has two electrons, even though it's out there in group 8 with all the other noble gases. It only has two valence electrons. If you want to represent the valence electrons, you use dots around the symbol. You can put two dots on a side for a grand total of 8. On the next page we discuss the octet rule, and atoms often gain or lose electrons when they're making ionic bonds, and they share electrons when they're making a covalent bond, and they were trying to fill their valence electrons, or their valence shell, full of electrons, and being full would be 8 electrons in their outer shell, and that's going to look like a noble gas. And of course there's an exception, which is hydrogen. Hydrogen tries to look like helium's electron configuration, and helium only has 2 electrons in its outer shell, so he only needs 2 to be filled, and then he'll be stable. Now some nonmetals can have actually more than 8 or less than 8. A notable exception is boron. I call him boron the moron. Boron only needs 6 electrons in its outer shell to be stable, so when it makes a molecule, it only is going to have 6. There are some more that have like 10 or up to 12 in some rare cases, and we'll talk about those later. Now we talk about what an ionic bond is. An ionic bond, as I mentioned before, is transferring electrons, and we have some vocabulary words on the screen here. It's formed between an element with a low ionization energy, and an ionization energy is the amount of energy required to remove an atom's outer electron, and the energy would be in like kilojoules per mole. And that electron that gets transferred is going to go to an element that has a high electron affinity. And electron affinity means that when the neutral atom gains an electron, it's going to release a lot of energy. And again, the energy that it releases is in the units of kilojoules per mole. And so basically what you're going to have is an element with a low ionization energy, which are metals. They're going to lose an electron, and it's going to go to a nonmetal, which has a high electron affinity, or it attracts that electron. So as it says on the screen, it's usually formed between a metal, which is on the left side of the periodic table, and a nonmetal, which is on the right side. And when I refer to the left side and the right side of the periodic table, I'm actually referring to a zigzag dark red line that's on most periodic tables that separates the metals from the nonmetals. It starts up at boron and it ends down at around polonium and astatine. On the next slide we have ionic bonding energies. So we're going to consider a reaction between sodium and chlorine, and you can see that 1 mole of sodium reacts with a half a mole of chlorine gas, and it produces 1 mole of sodium chloride, an ionic solid. And the delta H naught of formation, or the heat of formation, is negative 410.9 kilojoules per mole, which means that energy is released to the environment. So the reaction is exothermic, and we can infer that the sodium chloride is more stable than its constituent elements because this heat was released. Whenever energy is released in a reaction, it gets to a lower state, a lower energy state, and it's much more stable than it was before. Now here's another way of looking at the energy of the ionic bond formation. This reaction occurs in several steps. The first thing that has to happen is that the element sodium has to lose an electron, so you hit it with energy. That's the ionization energy, and the unit for this particular ionization energy is an electron volt, and I'll show you the conversion from an electron volt to a regular old joule later on. But 5.1 electron volts of ionization energy will remove that electron, and then the chlorine is going to gain that electron, and that's the electron affinity that I referred to on the previous slide, and it's going to release 3.6 electron volts of energy. And then when these ions are going to bond to each other, it releases another 5.2 electron volts of energy. So if you add all these up, you end up getting a net release of 3.7 electron volts. And in the middle of the screen you can see that you can convert electron volts into joules. We're only dealing with a very, very small amount of joules for an electron volt, so instead of 1 mole of atoms, you're looking at just one individual sodium atom. So that's why the conversion is rather small. But this just shows that when an ionic bond is formed, it's going to release energy. You have energy to remove the electron, that's a positive value, and then you have negative values of energy being released when chlorine gains the electron and when the sodium chloride bond is actually formed. On the next page we talk about lattice energy, and it's defined as the energy that is required to completely separate a mole of a solid ionic compound into gaseous ions. And from the table you can see that the lattice energy, or the energy to break it apart, is going to increase as the distance between the ions decreases. So as the ions are closer and closer together to each other, it's going to be more difficult to separate them. A good example to look at is something like lithium fluoride compared to lithium chloride or lithium iodide. So you go from LiF to LiCl to Li. If you look at the size of a fluorine atom, it's much smaller than a chlorine or an iodine. As you go down a group of elements, the atoms get bigger. So lithium fluoride ions are closer together in the lattice, in the crystal, compared to lithium iodide. So as you go from fluorine to chlorine to iodine, the atoms are getting bigger and bigger and bigger, so the lattice energy to separate them from each other to produce the gaseous ions actually decreases. So that's an inverse relationship. And then if you look at the next one, it says that the lattice energy increases as the charges on the ions increase. So if you have two positive ions bonded together, it's going to be less lattice energy than if you had like an ion with, oh, I just screwed that up, I'm sorry. I said two positive ions bonding to each other, and that's wrong. So if you have a positive 1 ion and a negative 1 ion bonding to each other, they would have less energy to separate them than if it were +2 and -2, or +3 and -3. So as the opposite charges on the ions increase, so will the lattice energy. So that's a direct relationship. And an example that you can look at is maybe sodium chloride versus magnesium chloride. Sodium chloride is a +1 and -1 ion, and it's 788 kilojoules per mole to break them apart into gaseous ions. But when you go to magnesium chloride, it's a +2 ion and a -1, and it goes up to 2,326 kilojoules per mole. Another thing you can look at is that the very first column on the left are all +1, -1 ions, and then you go to MgO and CaO and SRO. Those are all +2, -2, and then the last one, SCN, is scandium nitride. That's a +3 and a -3 ion bonded together, so it has the most lattice energy to break them apart. On the next page, I just give some more definitions. Metals, when they lose an electron, it's called a cation. They're always going to be smaller than they were before because they lost an electron, and their electron cloud's going to shrink. And a nonmetal, when it gains an electron, it's going to be larger than before, and we call those anions. And the number of electrons that an element needs to gain or lose depends on where it is located on the periodic table in comparison to the noble gas row. So they want to try to become more stable like a noble gas, so they're going to gain or lose electrons to sort of kind of go over to group 8 where the noble gases are located. So if you're in group 1, you're going to lose 1 electron. If you're in group 2, you're going to lose 2 electrons. If you're in group 3, you're going to lose 3 electrons. Now if you're in group 7, you have a tendency of just gaining 1. If you're in group 6, you're going to gain 2, and if you're in group 5, you're going to gain 3. And I have a lot of students that ask what happens when you're in group 4 because it's an equal distance to gain or lose electrons, and I tell them that usually in group 4 with like carbon and silicon, you're going to share electrons, so you don't really have to worry about gaining or losing electrons when you're in group 4 because they usually form molecules instead of ionic compounds. Now, there are groups of atoms that have charges as well, and they're called polyatomic ions, and we have an ion sheet with them all listed like sulfate and nitrate and ammonium and things like that, and those ions have to be memorized eventually. Now the atoms that are in a polyatomic ion are actually sharing electrons, so it's a covalent bond, but the group still has an overall charge. So you can have covalent bonds but still have a overall positive or negative charge, and the examples I show are the ammonium ion and the carbonate ion. Now we talk about covalent bonds rather quickly. An atom is going to share an electron to fill their valence shell, and it usually forms between 2 nonmetals, so that's 2 elements on the right side of that zigzag line. And a Lewis dot structure is going to represent a covalent bond with 2 dots in between the atoms, or sometimes the dots are replaced with lines. So here's a picture of chlorine atoms bonding to each other, and they're sharing those 2 electrons in between. And I have another picture here of the 2 dots being represented as a line. So if you see a line that represents 2 electrons, or you can just draw the 2 dots. And if you count how many electrons are around each of these atoms, they all have 8 if they're a nonmetal, and they have 2 if they're hydrogen, because 8 would make the octet rule, and so those elements would be stable, and hydrogen only needs 2 electrons around it to be stable. Then we have multiple covalent bonds. A single bond is just 2 electrons being shared. That would be 1 pair, but you have double bonds and triple bonds, so you can have 2 pairs or 3 pairs. There are no quadruple bonds. So I give the examples of hydrogen, oxygen, and nitrogen. That's the beginning of the word Hunkelbrief that we discuss in class, the diatomic elements. H is a single bond, O is a double bond, and N is a triple bond. All the other elements that are diatomic form single bonds. All the other Hunkelbriefs. So HONCLBRIF, that's single bond, double bond, triple bond, and then single, single, single for all the rest. Now we talk about bond length and bond strength. A single bond is the longest bond, so it's the easiest to break, so it's going to have the weakest strength, and then triple bonds are the shortest and they're the strongest. So single bonds are long and weak. Triple bonds are the shortest and strongest covalent bonds. Now, comparing covalent bonds to ionic bonds are much stronger than covalent bonds. Now we talk about bond polarity. The polarity of a bond describes how the electrons are being shared between the atoms, and there are 3 possibilities. You can have an equal amount of sharing between the atoms, and that's a nonpolar covalent bond, but you can have an unequal sharing of the electron pair, and that's a polar covalent bond, or you can have such a discrepancy in their attraction for that electron pair that we can consider that the electrons are transferred from the metal to the nonmetal, and that's classified as an ionic bond. Now, down below you have 3 pictures representing these polarities. So F2, the molecule, is perfectly nonpolar, but when hydrogen bonds to fluorine, there's more of an attraction for the electron pair on the fluorine side than the hydrogen side. So the fluorine side of the molecule becomes slightly negative, and then the hydrogen side becomes slightly positive. And there's a lowercase Greek letter delta that's shown on the screen. It's a delta positive and a delta negative. So one side is slightly positive, one side is slightly negative, and that's referred to as a dipole. So a dipole is another name for a polar molecule. And the last picture is lithium fluoride, an ionic compound. Lithium is a metal and fluorine is the nonmetal. And the arrow is actually pointing from the positive side to the negative side. So an arrow can show a dipole. So there's no real dipole in F2. There's a dipole in HF, and in lithium fluoride there's such a strong there's such a extreme difference between the attraction of the electron pair that lithium fluoride is considered to be ionic. Now, how can you tell what type of bond forms? Well, you have to do a difference in the electronegativity values. Now, all the electronegativity values for tests and quizzes and stuff like that will be given to you, but you need to basically know that metals have a low electronegativity and nonmetals have a high electronegativity. The most electronegative element is fluorine. So we have ranges of numbers from 0 to 4. We don't really have any elements with technically a 0 electronegativity. Electronegativity describes how attracted an element is to an electron pair when it forms a bond. You can kind of consider the noble gases not to have any attraction to electron pairs because they don't normally form compounds, but we've had some strange laboratory conditions where you can force chemical bonds to occur with noble gases, but for now you can consider like the noble gases won't have any electronegativity to worry about, and then it goes all the way up to fluorine with a value of 4. And the difference between the electronegativities will indicate whether a bond is going to be nonpolar, polar, or ionic. And there's no real sharp distinction between the bonding types, so even though it says here on the screen that a nonpolar bond would have a small difference between the electronegativity up to a difference of 0.4, there's not really a definite split between a bond being nonpolar and a bond being polar. So even though it's 0.4 and then polar starts at 0.5 all the way up to 2, and then it kind of transitions to ionic from any electronegativity difference above 2. It's sort of a slow change between being very nonpolar to barely polar to strongly polar, and then maybe weakly ionic to a high electronegativity difference, which would be, like 3.5 or something like that. That would be very strongly ionic. So there's a general blending from one type of polarity to another. And these electronegativity values, again, will be given, but it's kind of nice to know what the ranges are because it kind of helps you out if you don't want to just guess at what type of bond is going to be forming. So in the next part we have lattice energy and polarity. So lattice energy, again, as a reminder, is the energy to break the ions apart in a compound to gaseous ions. And so we have the lattice energy increasing as the electronegativity between the atoms in an ionic compound increases. So the more ionic a compound is, the more the lattice energy will become. That would be a direct relationship. Now we're going to have rules for drawing Lewis structures. Now there are a lot of rules that I'm going to go through on the screen, but you really can't get a grasp of the rules until you do the practice problems in class. So this PowerPoint presentation really doesn't give it justice on how to draw Lewis structures, and I don't have any examples in the slides. So I'm just going to go through the rules and hope you're in class when we're doing the practice problems. So rule number 1 for drawing a Lewis dot structure would be how many electrons are possible around an atom. Well, for hydrogen you only need 2, so it only is going to form a single bond, and then the second row elements and the third row elements typically are trying to get 8. Most elements want 8, but of course boron is the moron, he only needs 6. When you get down to the third and fourth row of elements, you can actually have more than 8 if there's extra electrons hanging around, and those extra electrons kind of overflow from the p orbitals into the unoccupied d orbitals. So if you have to fill in extra electrons more than 8, you can only do it to an element that's in the third or fourth row. So no element in the second row, that would be boron, carbon, nitrogen, oxygen, and fluorine. None of those elements would ever have any more than 8 electrons in their outer shell. So rule number 2, when you're drawing a Lewis structure, you have to arrange the atoms around a central atom. Usually the highest electronegative one is in the middle. Hydrogen can never be in the middle because of course it's only going to make one connection. So typically what we do is we just draw a single bond to everybody that's around a central atom, and then if it's an ionic compound you have to look at what, or if it's an ion, if it's an ion you have to look at what the charge is. If it's -1 you have to actually add an extra electron, and if it's +1 you'd have to take one electron away. So you can kind of arrange the elements sort of around a central atom and then distribute them keeping rule number 1 in mind. So hydrogens are going to need 2 electrons to be stable, and most other elements will need 8 to be stable. And if you have any extras, you can maybe give them to a third or fourth row element. But it could be a possibility that there are double and triple bonds as well. And again, you really need to do practice problems in class to get a hang of how to draw Lewis structures, and we do a ton of them. So rule number 3 on the next slide, it says for ionic compounds you have to indicate the charge of the ions. We usually put the ion in a bracket, and then we put the net charge on the outside. And for ionic compounds, they don't really share the electrons, they transfer them, so we don't need to draw lines in between them representing a covalent bond or the dots being equally distributed in between them, because that would represent covalent bonds, and these ionic compounds are just going to transfer all the metal ionic or the metal valence electrons to the nonmetal. So you end up basically with a metal without any electrons around it and a positive charge, and the nonmetals are going to be surrounded with 8 electrons and they would have a negative charge. Now if you have an odd number valence electron count, so like if you have a total of, let's say, 9 electrons or something like that, and you have to kind of cheat an element out of its octet rule of 8 electrons and you only give it 7, you don't want to cheat the element that has a higher electronegativity. So like fluorine is always going to try to get 8 electrons around it because it's the most attracted to the electrons in a bond with its high electronegativity of 4.0. So if you're going to cheat somebody, cheat the one that's less electronegative. And then there's a rule called the old Rule 5 resonance structures. If there's more than one way to draw a Lewis dot structure, you have to show them all. And I have an example of Lewis structures on the next slide or two. And then rule number 6 is kind of a funny rule. It says nature doesn't know anything about rules 1 through 5. So these rules are man-made rules about where we think the electrons are located, and nature doesn't really follow the rules sometimes, so these are kind of like Lewis theories about where they're going to be, and they're not really laws. And then, yeah, that's what it says. These are just models for us to use in order to represent the bonding. Alright, here's a page with the resonance. Resonance is our ability to draw more than one correct Lewis structure, and what I mean by correct is that everybody has their little octet. The example that I show is the ozone molecule. You can have the double bonded oxygens on the left side or the double bonded oxygens on the right side. Another common example is benzene. Benzene is a hydrocarbon compound with alternating double bonds between the corners of a 6-membered ring, and so you can have the double bonds actually shift from positions 1, 3, and 5 to 2, 4, and 6, and sometimes that double bond is just represented as being smeared all the way around this 6-membered ring, as shown in the last little picture, the hexagon with the circle in the middle. So you can have a resonance structure representing a molecule, but what's important to understand is that in nature there's not really 2 types of ozone molecules. This double bonded option of being on the left or the right is somewhere in between the resonance structures, so it's sort of smeared out between them. So if you really wanted to be describing it a little more accurately, it's sort of like there's a bond and a half on the left and a bond and a half on the right. It's not really a double bond, single bond. It's more, 1.5 bonds on the left and 1.5 bonds on the right. But when you have to draw the structure and you're forced to put the double bond somewhere, you end up getting resonance structures. And there could be 2 resonance structures like these examples, or there could be 3 resonance structures. Now we talk about formal charge, which is kind of an important topic. The formal charge of an atom is the charge that an atom in a molecule would have if all of the atoms had the same electronegativity, which means we're going to basically split the electrons that are shared evenly between the 2 atoms. Now to calculate formal charge, you can follow this formula, which is take the valence electrons of the element minus the number of bonds that it's making minus the lone pair of electrons that are around it. But there's a more of a visual way of figuring out what the formal charge is. Let me see if I can kind of describe it here in this example. We're going to figure out the formal charge on the carbon. So if you look at carbon right now, it typically has 4 valence electrons. From looking at the periodic table, it's in group 4. So you start out with 4, and then you can kind of think of splitting the electrons for the carbon evenly that it's sharing with the nitrogen. So you see a triple bond for the nitrogen and carbon connection. And what we can do is we can kind of think to ourselves, okay, carbon has 2 electrons that are lone pairs on the far left side, and then if you evenly split that triple bond, it's going to have 3 more electrons on it. So you basically are going to take the valence electrons, which are 4, minus the 5 electrons that we've evenly distributed on the carbon. So you have 4 minus 5, and you get a formal charge of -1. And if you look at the right side, you have the nitrogen with its 2 lone electrons on the far right that are in blue, and then again we've evenly distributed the triple bond, which are 6 electrons altogether, but 3 of them go to carbon and 3 of them go to nitrogen. So you have the valence electrons of nitrogen, which is 5, again from the periodic table it's in group 5, and then you're going to basically subtract out the 5 electrons that we've evenly distributed from the triple bond, and then you have the lone pairs. So it ends up that nitrogen is 5 minus 5, which is 0. Now you can always kind of double check your answer, because if you add up all the formal charges, that's going to be the net charge on the molecule. In this case, it's the cyanide ion, which has a net -1 charge, as shown outside the brackets. So when you look at carbon's formal charge of -1 and nitrogen's formal charge of 0, you end up getting that net charge on the ion. Now we do a lot of examples of formal charge, and it's not that complicated of a topic, and it's kind of hard to show just in a slideshow presentation, but in class it's not that hard to kind of break the bonds in half and give everybody their electrons and calculate it. On the next page, it says the most stable Lewis structure has the smallest formal charge on each atom and the most negative formal charge on the most electronegative atoms. So if there's a debate on which resonance structure is the most stable, you kind of look at the electronegativity of the elements and calculate the formal charge. And so if you have an option, let's say, of fluorine in a molecule having a -1 formal charge or a +1 formal charge, well, fluorine being very electronegative is most likely going to have a negative formal charge. And if you have an option of a molecule having, let's say, a formal charge of +1 and -1 on 2 elements, or 0 formal charge on one and 0 formal charge on the other, you're probably going to have the more stable Lewis structure being the one with no formal charge on everybody, as opposed to +1 on somebody and -1 on another. So formal charges aren't real charges on the atoms, they're just our way to try to figure out which Lewis structure is the more correct. And again, we do a lot of examples in class with practice problems, and it makes it a little easier to understand. Now we're going to talk about strengths of covalent bonds. The energy required to break a bond is called the bond dissociation enthalpy, and you have to put in energy to break bonds, and so that's a positive value. And the bond dissociation energy is represented with a capital letter D. So when you put in energy, that's an endothermic positive D. When bonds form, they release energy, and so that's going to be a negative value. So for a chlorine molecule, we have the example on the screen. If you have chlorine gas, the diatomic element chlorine, if you break it apart into 2 individual chlorine atoms, that's going to be breaking a chlorine-chlorine bond. It's going to be a positive 242 kilojoules. So when more than one bond is broken, you actually can get a fraction of the delta H. So if you look at the example, it says you have methane, which has 4 carbon-hydrogen bonds, and the total amount of energy to break all 4 bonds is 1,660 kilojoules. So if you look at 1/4 of that, each individual carbon-hydrogen bond would be about 415 kilojoules of heat. And again, these are positive numbers. So you can kind of estimate what the energy of one single carbon-hydrogen bond is by just taking the delta H divided by 4. Now this is a chart which shows all the bond enthalpies for different atoms when they're bonded together. Now it's important to realize that these are average bond enthalpies. See, on the previous slide we had a carbon-hydrogen bond in methane being 415 kilojoules, but in this chart it shows that a carbon-hydrogen bond is 413 kilojoules per mole. Well, what's up with that? Well, if you take all the carbon-hydrogen bonds in every molecule that they've tested, it kind of depends on what the neighboring bonds or the neighboring molecule is. So sometimes a carbon-hydrogen bond is easier to break if, let's say, there's a highly electronegative element next to it or something like that. So on average, all the carbon-hydrogen bonds are 413, but for a particular molecule like methane, we know it's 415. Now, the energy released when a bond forms is just the negative value shown in the table. So if you break a carbon-hydrogen bond, it's 413 kilojoules positive. If you form a carbon-hydrogen bond in a molecule, it will release on average 413. That would be a negative value. So this table is used a lot because we're going to actually use the bond enthalpies to calculate the enthalpy of a reaction. So here it is on the next slide. It says using D, the bond enthalpy, to determine the delta H of a reaction. All you need to do is take the bonds that are broken minus the bonds that are formed. So usually delta H is the products minus the reactants. Now we have the bonds that are broken minus the bonds that are formed. Bonds that are broken are positive values, and bonds that are formed are technically negative values, but we're going to just look up the values on the previous page. So all of those are positive values. So we're just going to take the numbers that are shown for the bonds that are broken and subtract the numbers that are shown in the chart for the bonds that are formed. Here's the example. We have methane plus chlorine gas turns into CH3Cl plus HCl. So what have we done? We broke off one of the carbon-hydrogen bonds, and we broke apart the chlorine-chlorine bond, and we formed a carbon-chlorine bond, and we formed a hydrogen-chlorine bond. So we're going to take the bonds that are broken, those numbers, and we're going to subtract the bonds that are formed. And what numbers do you see? The carbon-hydrogen bond broken is 413. The chlorine-chlorine bond broken is 242. We're going to subtract out the values shown in the chart on the previous slide of a carbon-chlorine bond forming minus a hydrogen-chlorine forming. And you end up getting a negative value, a negative 104 kilojoules. And so it's exothermic, which means that the bonds that are formed are actually stronger than the bonds that are broken. So it's more stable. It releases energy. Now, this above result is consistent with Hess's law. We used Hess's law to find delta H's of reactions doing products minus reactants. You can do the same thing for bonds broken minus bonds formed. And again, as always, we do a lot of practice problems in class.